Right, we are nearing the end. The end is in sight. We are on the home stretch. We just have a short stop off in integrating vectors, and then we're there. We are home free. The end. Hello, everybody. And this should be a relatively nice one to kind of finish on. Because if you think about all of the things that we've done with differentiation and integration along the way, and how we've looked at differentiation and how they work with vectors, then there will be no major surprises for how integration and vectors work either. Okay? So we're going to take a look through these final few things, and then we will kind of just we'll bask in the success that is finishing Year 13 mechanics. Okay? So, let's get going. Let's get started. As I said, the same way that we have looked to differentiate vectors, so if we've had a vector to measure something's position, and it was a product of 3t squared for my I direction, and maybe sine 2t, same variable, for my j direction, then we can differentiate to find our velocity, and we just differentiate the top and bottom parts of the vector separately. So differentiating 3t squared, we would get 6t. And differentiating sine 2t, we would get 2 cos 2t. Okay? And because we know that when we differentiate, we go from our position to our velocity to our acceleration. So when we do this, when we're differentiating, and because integration is the reverse of differentiating, we should have that we get kind of back to where we started. Okay? So if I were to take this expression for my velocity and integrate it, what I should end up with is my position. Okay? So my position, which will be the integral of my velocity vector, is just going to be the integral of 6t and 2 cos 2t, like that. And we're integrating with respect to t. And how we integrate the parts of our vector depends on what integration skills we've needed to do all the integration problems we've done so far. Integrating 6t, we would just increase the power by 1 and divide by that new power, which will give us 3t squared. And integrating a trig function, well, cos would go to sine, it would go back to sine, and we do like reverse chain rule on the part in the middle. So we essentially divide by the differential of that bracketed part there. So we would get back to sine 2t. But one thing that we will have to be careful in terms of integration is this constant. Okay? Now, when we integrate a normal expression, not a vector expression, but a normal expression, we always have some kind of constant at the end that we have to add in if we're doing a non-evaluated integral. Definite integral, I think, off the top of my head. Can't remember, never can remember. But we have this plus constant, okay? Now, when we're talking about vectors, our position vector, this is a vector, this will also be a vector. Okay, so our constant of integration is also a vector. Okay. Now, if we're evaluating an integral, we don't need to find our constant of integration. But if we are not, and say we've got some information that it's, at this position at a time t equals 0, then we will need to use that to find out what our constants of integration are. Okay? So let's take a look at the problem that we've got on here to start off with. We've got a particle moving in a plane, and at a time t seconds, its velocity is given by that expression written with i's and j's. Okay? And we're told that t has got to be greater than or equal to 0. When t is 0, the position vector of p with respect to a fixed origin is 2i negative 3j. And we want to find the position vector of p at a time t seconds. So we're trying to find the kind of generic formula for our position vector here. Okay? So we have our velocity. We want to find our position. So we're going to have to integrate that expression to get our position vector. Hello to the people there. Hello. So we integrate this. Power increases by 1, so we get a power of 2. Divide by the new power. Power increases by 1, we get a 3. Divide by that new power. Okay? And don't forget to include your constant of integration, which, as we've said, because we're dealing with vectors, is a vector. So we get this beast here. Now we've got to use the information that we've got to figure out what our constant of integration is. Now in this case, we're told that when t is 0, the position vector is 2i take away 3j. So when t is 0, substituting 0 into this vector, we get that our position vector is 0, 0 plus our constant vector. And that should equal 2, negative 3, because that's what we're told our position vector is when t equals 0. So that means that our constant vector is 2, negative 3. Okay? And so our position vector at any time t is going to be this expression that we found before from integrating, plus our constant vector, which we found by substituting in the information we were given in the question. Okay? And you can merge the two vectors together to give you this expression in one complete vector. Okay? And in terms of this thing, when t is 0, your constant vector here, this could be thought of as like your starting position. Okay? It just means that we start at a point which is 2 across and 3 back from the origin. Okay? So, very much like the ideas that we did with differentiation, we're just using a different process. We're using integration instead. Okay? So we've got some additional problems that we can have a look at. We've got particle moving in a plane so that its acceleration is 4i take away 2tj. When t is 3, the velocity is 6i, and the position vector is that, 20i plus 3j, with respect to a fixed origin. Okay, and it should always say with respect to a fixed origin, because that's how position vectors work. They are a distance away from a fixed origin point. We want to find the angle between the direction of motion in P and I when t is equal to 2. And we want to find the distance of P from O when t is equal to 0. Okay? So, before we get cracking with all of our integration, survey the problem, make sure that you know what information that you've got. We've got acceleration 4I negative 2tj, and you can use the I and j notation. That is not a problem. It's just my personal preference is to use the column notation. We're told that when t is equal to 3, our velocity vector is just 6i, no j's. And when t is 3, our position vector, which we normally use the letter r, is 20i and 3j. To check I've not mixed anything. Nope, don't think so. So we want to find the angle between the direction of motion of p and I when t is equal to 2. Right. Now, we've got our acceleration here. We've got information for our velocity, and we've got information for our position as well. We're going to have to do a little bit of integrating to get our velocity, because we're talking about direction of motion, okay? And for part B, we're going to have to then integrate a second time to have a go at finding the distance of P from O when T is equal to 0. Okay. So what we're looking to find is a velocity vector. Remember your constants of integration. A position vector after that. Again, remembering your constant of integration. And then seeing how we can answer those problems. Okay. What I'm going to do is I'm going to give you just a couple of minutes, maybe 3 or 4 minutes, just to have a go at that first part, okay? And then we will go from there. All right. So what should we look to have done in this kind of time? Well, we should have looked to have integrated this to give us our velocity vector. So integrating 4, we just get 4t. Power increases by 1, so that would become 2. Divide by that, we get negative t squared. And we have our constant vector as well. Now, when t is equal to 3, we get a velocity of 6, 0. Okay, so we're going to continue this down here. When t is equal to 3, we get 4 times 3, negative 3 squared. Okay, and I've put brackets around the 3 squared because that bit should happen first. It's going to be t squared, then make it negative. It's not negative, well, negative t all squared. Okay, plus our constant. And that is equal to 6, 0. So 4 times 3 is 12. 3 squared is 9, make it negative. So that plus c is equal to 6, 0, which means that c is going to be equal to this vector take away this vector. So it's going to be negative 6 and then 9. Okay. So we have our velocity vector, which is now going to be 4t take away 6 and 9 take away t squared. Okay. Now, what we want to find is the angle between the direction of motion of p and I when t is equal to 2. So, oh, hang on, I've realised I've gone off paper. There we go. So, you can almost imagine that I've got my eyes here. I've got some direction of motion, which is disappearing off into the ether, and I want to find the angle between the direction of motion and this line here. Okay? So when t is equal to 2, well, we would have to substitute that information in first. We would have to find out what this vector is equal to when t is equal to 2, and then look to draw that vector out, use a little bit of trigonometry to do so, and then, away we go. So let's see what that should look like. Okay? So when t is equal to 2, our velocity vector is just going to be 8 take away 6, which is 2, 9 take away 4, which is 5. So it just means like 2 across, 5 up, so it's going like something like that. And we're looking to find that angle there. Okay, we know that that is 5, that is 2. So we can use some trigonometry like we've done just here to get our angle. Okay. Now for part B, the distance of P from O when t is equal to 0. So that's thinking of like almost like our starting position. Okay. We're going to need to integrate again to find our position vector, and then use the second piece of information to find out our constant of integration again. And then, once we've got that, then we can use I've just pointed at my screen. You can't even see my screen. Use this information here to find the distance of P from 0. You can't see my hands. You can see my screen. You can't see my hands. So yeah. We'll go for another 3 minutes for that part B, and then we'll see how we're doing. remember to make sure that you substitute the right information in the right places. So we're using the t equals 3 information to find our constant of integration. And then we're using the t equals 0 stuff to find out the answer of our question. All right. So, integral of our velocity vector gives us our position vector. Okay, we integrate with respect to t. We get our position vector, which will be 4t integrated is going to give us 2t squared. That will just become 6t. And 9 will become 9t. And this will become take away t cubed over 3 plus our constant vector. And what's the information that we're using? We're using that is 20 and 3 when t is equal to 3. So we would substitute 3 into this bit here and put it equal to 23 to find out what our constant vector is, just like we did with our vector for velocity up here. And then we want the distance of P from O when t is equal to 0. So we would have our expression for our position vector, including our constant, and then we would substitute t is 0 into it to find out what the distance is in terms of a vector. So let's have a look at those, because I'm run out of page. So we've got the 2t squared, take away the 6t in that second line. We've got the 9t, take away t cubed over 3, plus constant. If t equals 3, we get 0, 18 from this part of our vector, plus c, and that is equal to 20 and 3, which means that when we do this vector, the 20 and 3, take away this vector, the 0 and 18, we get 20 and negative 15. So our position vector for the whole thing is going to look a little bit like this. Okay? And when t is 0, we substitute that in to find out our distance as a vector. But distance isn't a vector measurement, okay? A vector tells us displacement from an original point. Distance is the scalar of that vector. So we would need to perform Pythagoras on that vector to get an actual measurement for our distance as opposed to our displacement from 0, okay? So hopefully this is all starting to kind of click in a little bit now. And in true fashion, we then jump back to 2013 for an exam style question. Okay. Wording is a little bit grainy, but never mind. Hopefully you guys can still read it. We've got velocity of a particle, which is 4t minus 5i plus 3j. When t is 0, the position vector is given as that, relative to a fixed origin. Find the value of t when the velocity of p is parallel to the j vector. It's an interesting little problem to start us off with, just for 1 mark. Find an expression for the position vector of p at a time t. And then we've got a second particle, and these two particles will collide at the point where we have a position vector di plus 14j meters, and we've got the value of c we need to find and the value of d that we need to find, and we've got all of those parts kind of coming in together. So, in theory, in an exam, this thing should take us roughly 10 minutes. Okay? Now, in the sake of challenge, we're going to shave 2 minutes off. We had a nightmare on one of the stats questions because stats is a nightmare. And then we've left ourselves with 2 minutes short. Okay? So we're going to see what we can manage to do with those 8 minutes. And I'm going to stop it after 4 just to kind of give us a little bit of headway with those first two parts. Okay? So here we go. It's our last one. It's our last question. You can do this. Off we go. I do not know how any of the papers would have looked. I wouldn't have known until the day. And even when I say the day, it would be after you had sat your exam. Well, no, when is it we get them? We get them, I think something like 24 hours, 48 hours after you guys have done the assessment, I think. So, yeah. My crystal ball, which is very, very malfunctional, is telling me that there would have been a nightmare stats question. Okay, we're getting close to the halfway mark. I'm going to get myself a set of fresh paper, or a column of fresh paper. Alright, we're counting down to 4. Oh, oh, close. Never mind. So the first few parts. Okay. So part A, when we have the value of t for the velocity of p parallel to the vector j. Okay. Well, if it's going to be parallel to j, then what I want is for this to be a multiple of this. Okay, I want it to be some kind of multiple of that, which means that I want 4t take away 5 to equal 0. Okay, so that just means that there's no kind of movement across. All of our movement is going upwards. Okay, so 4t take away 5 is equal to 0. That means that 4t is equal to 5, and t is equal to 4/5. Okay, so when t is 4/5, our velocity of our particle is just heading upwards, so we are parallel with the j vector. For part B, an expression for the position vector of p at a time t seconds. Okay, well, our velocity vector is 4t take away 5 and 3. We want to integrate v with respect to t, which means that we're integrating 4t take away 5 and 3 with respect to t. And I'm writing my workings here as 5/4. Yes, yes, good spot. Good spot. I'm trying to write my workings as more like how I would write them in terms of actually writing things down. So integral of 4t take away 5, we're going to get 2t squared. That's going to become 5t. And the integral of 3 just becomes 3t plus our constant vector. We then, what's the information that we have to find out our constant vector? We have that when t is equal to 0, our position vector is 2, 5. Okay? So when t is equal to 0, all of that is going to be equal to 0. So 2, 5 equals 0, 0 plus c means that c is equal to 2, 5. Okay? So the expression for the position vector is going to be this thing, 2t squared take away 5t, plus this thing, and then 3t plus 5. Just like that. Okay? Now, we're going to potentially need that for our second part, which is talking about a second particle. And we've got the position vector, and we've got another constant velocity vector, and we have the particles p and q collide at the point where the position vector is this. We want to find the value of c and the value of d, and we have 4 minutes left to go. Here we are. All right. So I put a little white box up so that I could start to scribble some things away and see how things go. So what I started off by doing was to kind of write out what the velocity vector was for my second particle. I just called it VQ to stand for the velocity of Q. I wrote out what the information was that they gave me. I found the position vector of Q by doing a little bit of integration, finding out what our constant of integration was. I gave it a different letter other than C because C had already been used. And I didn't give it the letter D because D had been used later on as well, so I just gave it K. And when T is equal to 0, both of those things are equal to 0, so we just have that K is 11.2. So this would be my position vector at this point. And so when particles P and Q collide, then we have the position vector of P and the position vector of Q, which you can see now, which should be equal to one another. Okay, and that should give us some equations that we can then look to try and solve. Okay, because we know that as well as those two position vectors being equal to one another, they will also be equal to the position vector D14. And so we'll then be able to mix and match things up to be able to get all the things that we want. Okay? So let's have a look. So T is 5/4. Excellent. 2t squared minus 5t plus 2. 3t plus 5. Excellent. So that's our first 5 marks all done. Our position vector for Q, we have 11 take away 2t, yeah, and we have 2 plus ct. They've written it awkwardly, but they've then rearranged it afterwards to get this line. Okay. And then what they said is that the position vector of P is equal to the position vector of Q, which is equal to D and 14J. Now I've written that slightly differently on my next line, which looks a little bit like that, just at the bottom here. And then we're looking to find out all of the different bits of information that we can from this. So we can find the time that they collide by looking at 3t plus 5 is equal to 14. Okay, so that gives us our time of collision. Once we know what the time of collision is, we can use the value of t to work out our value of c. And once we know our value of c, that's one part of done. We then just want to find the value of d, and we can do that by looking at this section up here, because we know what value of t that the two particles collide. Okay. You can see that there are a couple of alternates in here as well, where instead of using the linear equation, people decide to use the quadratic equation, which, I mean, you can, but if you've got a linear equation to use, why wouldn't you use that? But yeah, there we go. We have our value of t, which is just going to be 3. We have our value of c, which we can get from this part down here, which is 4. And then using our value of t in the upper part here, we get that d will be equal to 5. Okay? So a 10 marker in about 8 minutes should be pretty good, okay? It's doable, definitely. Although, and that gives you then a couple of minutes to focus more on a horrendous stats question. Who knows? Right. And then you can finally breathe a sigh of relief. Because, short of an exercise, you have reached the end of maths at A level. And you can give yourself a round of applause. I got the only thing that I can really say at this point is well done. Okay, you did really, really well to get to this point. You worked really, really hard, and that's it. There's all the little bits done. Okay, it's a monumental effort. Yeah, the end of maths at A level. There is always more maths. But seriously, well done for getting to this point. And yeah, we missing an obelisk, yeah, and some magic potion along the way as well. Yeah, just well done. Yeah, I kind of said everything that I needed to say when we were in school. It's a comic, Lucy. Asterix and Obelix is a comic from a while ago. I don't know if they still make them. Check it out. Use some of your spare time at the moment to check it out. But yeah, I'm going to sign off at this point. I am going to be producing some extra little streams for my Year 12 further mathematicians who need some of the stuff that we will have done at in Year 13. They need it a little bit fast tracked so that they can access some of the stuff in Year 13 further maths when we need it. So you feel free to watch those or tune into some of those. They'll be going over some of the differentiation and integration skills. If you're bored, you're more than welcome to come and watch. But yeah, it's been really nice. I will catch you at some point, hopefully in the future. Okay? And I'm going to say goodbye. Bye-bye.